Yeah.
So welcome back. It's 9/11. We'll pause for a moment of silence and just a couple of moments here. So on September 11th, 2001, there was a really bad thing that happened in the United States of America, and it changed our world for many of us. Remember that there's a one-time extension of the Module 1 assessment for your first attempt until 11:59 p.m. tonight. And if you have not logged your first attempt of the Module 1 assessment by 11:59 p.m. tonight, this is the only time I will extend the deadline for module assessments. The intent here is to be able to post credit in each module. Once we finish the assessment and we're ready to review the items, by that time I will have posted your scores, your credit for all the other things in that module. So you can go here and you'll see total possible, right? And it says divide total earned by this number and then multiply by 100. So this is total possible. It'll show a number here, like if the first points possible in module 1 is 20 points, right? And then the total possible, you're never using weighted total. You never reference that. You're always looking at total earned and total possible. So you take the number listed in total earned, divide by total possible, right? If you click the description here for total possible, it gives you another hint that's consistent. Divide the total earned by this number. So if you have the total possible number, you need to look up the total earned number and vice versa. You're always dividing earned by possible and then multiplying by 100. So if you get 18 divided by 20, right? 18 divided by 20, let's say you have 18 total, and here's my calculator, and it's hidden by the screen here. So if I go to a standard calculator and I take 18 divided by 20, that'll give me this times 100. I have a 90% average in the course, right? So this is one thing that I don't want to take a beating from so many students at the end of the semester who legitimately say, wow, it takes longer to get, stuff back. So I do need everybody's help with this. Please be sure that if you're one of the 8 people in this class who have not attempted your module assessment, you need to finish by 11:59 p.m. tonight, okay? Any questions about this before we get started? I'm now going to show, so what we'll display when you refresh is the next module. What we're going to do today for the balance of the time is we're going to start with our introduction of module 2 material, and then on Wednesday, we'll go over the items on the module 1 assessment and how to reconcile, okay? So we're going to reverse this order of what we do in the class and how we do just this one time for folks who didn't get the notice or your schedule didn't allow, so that you can get that first attempt in. Any questions before we continue? All right, so in our second module, we're going to take that new understanding of binary and hexadecimal numbers, and we're actually going to start working with the first round or most basic Boolean operators, right? So these are logical operators, and, or, and not. Describe essentials, including the order of operations. When we say order of operations, if you have more than one of those operators in the mix, just everybody think back to your 6th grade math, right? 6th grade math course. You're in the 6th grade, we're doing math. If you have a calculation with several operators, and multiplication, division, addition, and subtraction are in the mix, which ones, can you do them all in order from left to right as they're written, or do you have to do some of them before you do others? Does anybody remember? Have to do some before you do others. That's correct. It's called, there's an old acronym in some places. We learned My Dear Aunt Sally, MDAS. So multiply, divide before subtract and add. if there aren't parentheses. Now, if you have parentheses to offset, then that's a different animal altogether. So we'll be getting into that. There's a negative transfer. When we say negative transfer, we're going to say that there's a mental stumbling block, if you will, for one of the operators. We've hinted at it so far. We've just hinted at it, but we're going to go into deeper. We're going to take a deeper dive on that so that you're really intentional about using one of these Boolean operators very carefully until it becomes a habit, right? So because of what we learned in algebra, and because of what we learned for so many years, you have to kind of unlearn, and it's a linguistic thing. It's a trick that your brain plays on you, because we don't want people getting frustrated. We're going to explain how the pattern of output differs between and, or, and not. So what's the intent here? We want you to be able to, at a glance, look at a pattern of ones and zeros and go, oh, I know what's going on here. Right? Because that's what computers do. You visually have a supercomputer. The visual cortex of your brain is actually quite advanced, more so than a supercomputer. There have been studies that show that humans can pick up on visual differences and changes very, very well, right? So we're going to take advantage of your own computing capacity between your ears. We'll distinguish between interface and implementation views of a logic gate diagram. So we're going to start drawing basic digital components. We're going to build our first digital components. And that's really cool, because when you start using these, it's sort of like Legos. They only fit a certain way. If you observe certain rules or restrictions, right? They only go together a certain way. But it's a predictable way and it's a sensible way. And then after you start getting used to it, you're like, oh, this is like Legos. I can build my own computer with Legos. And that's the intent here. You're going to use an organizing method called a truth table. A truth table is going to appear differently in this course than it does in your discrete math course. Do we have any students who have completed or are taking now the discrete mathematics course? Anyone?
I have completed course already.
You have completed, is this Zeden that said that?
Yeah.
Okay, so in your case, what's going to happen, Zeden, is that we're going to call out a difference between the technology industry and mathematics as an academic subject, right? So the way that truth tables, you work with truth tables in discrete math, correct?
Yeah, I did.
Okay, all right. So the truth tables are going to be arranged a little differently. And that's because by convention, we work it in a different manner. And symbolically, we do some things a little differently as well. And is there anyone else besides Zeden that's had discrete math? So Zeden, what I'd like to ask you is, if you find that you're not getting some solutions correctly, I want you to reach out to me and let's take a look, because it could be that there were some practices that you picked up in discrete math that the context is different. I don't know if I'm making sense, but what would be a good analogy? How many of you know, well, you can use a laptop for all sorts of purposes. And basically what you have is a set of concepts, and in different contexts, you're going to operate differently. Let's just leave it at that for now. We said we're going to create simple combinations of gates to create compound logic gates. We would start calling these Boolean functions. So if you have more than one operator, it's considered a good practice, right, to use the terms consistently. If you have a Boolean operator, we're talking about and, or, and not, and, or, and not. If we're talking about a function, the understanding is that there's more than one of those in the mix. There's a shorthand. It's called canonical. when you start working with truth tables, you're gonna go, oh my gosh, this is so complicated. Well, there's a way to distill it down so that you can take a very complex Boolean function, or you can take a compound logic gate, right? Complex logic gate, and you can distill its behavior down into a very simple statement that's real easy to understand. But that's called a canonical or reverse canonical expression. And that's something we'll explore in greater depth here. So if I give you the implementation view of a logic gate, I want you to be able to derive the software equivalent using operators. One of the cool things about this course is that you kind of have more than one palette to work with, so to speak. If doing things in code is confusing, then doing things graphically with physical logic gates might click better. But we want you to be able to translate from one mode to the other, because what you're going to find is that a lot of times code that's used over and over again should be converted into a physical digital component, which is 1,000 times or more efficient. So a hardware component that does the same thing is 1,000 times or more efficient than code. Let me say that again. If there's a thing that's done over and over and over again with code, and you build a digital component, that's something you can put on the shelf and sell and make $1 million. Because now it's a gadget, and there's a chip for it, and it just works. And that's the cool part of our whole industry. Given the software equivalent, derive the hardware equivalent. So we're going to ask you to work in reverse. So we'll give you the hardware equivalent, ask you to give us the software. We'll give you the software equivalent, ask you to give us the hardware. And then apply the concepts to create a simple compound logic gate using the HDL simulator. Now, it's very important to understand this module, if you get it right, you'll be in an excellent place to go to module 3. If you do not take quality time in module 2, by the time you get to module 3, there are a few basic steps. If you miss any one of them, the entire outcome of your solution is blown, and it doesn't work. And you get all the questions associated with it wrong on solutions and assessments, okay? So it's a very simple but rigid way of working, and I'm going to model that and ask you to, for the short term, not take any shortcuts, okay? So let's get started. Can everyone see the screen?
Yeah.
Okay. Let me make sure I have this up to date. If I could share just a couple of brief moments of silence for 9/11 and all of the losses that followed after 9/11. Okay, so there is a very famous quote by Albert Einstein that it's good to simplify things, but not make them simpler, right? So there are some things that we're going to do that you may be tempted to just take shortcuts or simplify, and because we're working with different kinds of concepts, it's really important to avoid that temptation. So we mentioned and, or, and not. And one of the things that we said about and, linguistically, and would tend to imply addition. If I take the numbers 2 and 3 and 6, what does that give me? Linguistically, we hear that phrase and we think, okay, I'm adding. 2 and 3 and 6. Unless I'm very specific with my language and I say I'm going to multiply 2, 3, and 6, right? But a lot of times when we hear the word and, you know, in the back of our head, and is often associated with when we're summing things. So I have $5 and $20 and we do this without even thinking about it. It's instinct for us. And the point I'm trying to make is that that instinct can bite us. And is the multiplication operator. And it is distinctly different. It has a round dot as a symbol, or is the plus sign, or is the addition, right? So when we're doing mathematical calculations, whenever and or are in the mix, we're multiplying or adding on a binary level. The not, we've said, is already a wild card. So whatever result you have, if it's knotted, it's reversed. So if it's not 0, it's 1. If it's not 1, it's 0, and it's just that simple. But in a function, not becomes like the spice or secret sauce in a special cuisine. You know, it only takes a few spices, and you have a whole different outcome, right? So for those of you that are into cuisine and cooking, you know what I'm talking about. All it takes are a few different spices, and now it's a whole different flavor, right? And knots are like those. It's like those wild cards. Depending on where you put them and how you put them, wow, you get amazing results. We're going to talk more about physical materials in a later module, but one of the things that we want you to understand is that the Boolean operators have physical equivalents that we call logic gates. And those either turn on or off the value that's stored or produced. And it's just that simple. So whenever you hear logic gate, you got to think, okay, this is hardware, that's physical. I can touch this. I can look at it and it's a chip, right? It's a chip. So it's made out of logic gates. That's where you see logic gates. Whenever we talk about Boolean statements, that's a software kind of thing. Physical gate, there are symbols that are used to represent each of these logic gates or Boolean functions, right? And a truth table is a way of rendering all the possible combinations when those operators are used. Let me say that again. A truth table is a framework we use, it's a tool that we use to render all of the possible outcomes when you have different inputs, okay? So in the digital world, you have inputs, there's some kind of calculation or computation, and then you have outputs, right? And that's part of von Neumann's model, basic model of a computer. You have digital information that's fed into a computer, there's some calculations or computation, and then you have output. And at the most basic level, truth tables help us understand how these components work in a very basic manner. And the thing to understand is that the truth tables are, there's a strong relationship between the truth tables and probability. Do we have any poker players in our class today? Any card players? Any gamblers?
Oh, gosh.
Gamblers, okay. So probability, right? If I ask you to pull a card from a deck of cards and I tell you what's the chance that you're going to pull a heart, there are 13 cards that are hearts. Everybody understand what I'm talking about? And there's 13 that are clubs and 13 that are diamonds and 13 that are spades. So the probability that you're going to pull, if you shuffle those cards, the probability that you're going to pull a heart is 1 in 4, because 1 in 4 cards in the deck are hearts of any kind, right? So what you're going to see is that there's a strong correlation between truth tables. When we finish the end of next module, possibly this module, we're going to show you how casinos can take logic gates and they can design some of their slot machines, some of their resources, so that by touching a button, you're a lot less likely to win. But if they need to hook you, and I mean, this is one of the things about my course that I find the most fascinating. If you construct the circuitry behind that slot machine in a different manner, you're going to increase the chances that you're going to win, which is great if you have a novice. If you have someone new to gambling, what you want to do as a casino is pique their interest and hook them so that you have a repeat customer, right? You want people to come back and spend more money. And it's kind of a drug. So if you win, you're going to feel lucky. And then all they got to do is turn a dial or push a button and use the other chip. And now all of a sudden, I'm not saying they do this intentionally. I am saying that there are ways to rig the game with logic gates so that anybody could push a button, and now it's a lot harder to do something, right? And this applies to gaming environments. So this is actually a really cool thing to learn if you're learning about the gaming industry and how it's so easy to kill the boss on this level, but it's not so easy to kill the boss on that other level. So when we look at the basics of and, or, and not, one of the most common ways to identify or label inputs is with a single letter. And I hate that. You should use more descriptive labels, but for the time being, it's a very common practice to take the inputs and then label them with letters. So if you have a logic gate that has ABC inputs, that means it has 3 inputs, and then there's a single output, okay? So one thing that's common about our logic gates is that no matter how many inputs you have, there's only one output. And it's a 1 or a 0 that's rendered. That's something that's common among all logic gates and Boolean operators. The other thing that I'd tell you is that the not operator has only one input. So the one exception to that statement is not receives one input, and then it only renders the reverse out. So it's the one exception to that statement. Nots will always have only one input and only one output. Ands, or, and nots can have multiples, depending on how you design them, okay? We've already said that the logical result of ands is that when all of the input values are a 1, then the output is a 1. So every single input must be a 1 in order for, so input A and input B and input C must all be a 1 in order for the output to be a 1. But with an OR, if you had a 4 input OR, input A or input B or input C or input D could be a 1, and the output would automatically be a 1, right? So those behaviors are really important to understand on a simple level, and we talked about that a bit on Friday, right? In terms of the order of operations, this is what we're familiar with. What do we do? Add first or multiply first? According to the rules of operators in mathematics, we know and are familiar with. This isn't Boolean, this is just regular math. We multiply first, right? So we're going to get 24, and then we add 5 to it. Does everybody see what's going on there? So, my dear Aunt Sally. Now, the other thing that I'd share with you is, do you always do multiplication before you do division, or is it either multiplication and division before addition and subtraction? In other words, is it multiplication, division, addition, and subtraction, and we always do the subtraction last? Or is it just multiplication and division has to be performed together, doesn't matter which, before we do addition and subtraction? Doesn't matter which.
Yes, the latter.
It's the latter of the two, right? So when you're doing math, the thing to understand is that even though that order of operations is kind of, it's robotically, people know it's multiplication, division, addition, and subtraction. It's really multiplication and division as a group of operators. They have to be done first, depending on where they're encountered in the equation, and then addition and subtraction. So you notice the difference here, right? This is an incorrect result. If we multiply 11 times 44, that doesn't work. That's an incorrect way of doing it, unless we intentionally use parentheses. Now, if I use parentheses around this, and this is something about software and hardware, we can isolate a set of operators and see that they're calculated first, and then the other operator is done. And in a case where you use parentheses, this is the correct result for 44. If I said this is the answer to this is 44, that would be incorrect, because it means I'd be adding 5 and 6, but there's no parentheses. But if I add the two first, because that has to be done inside, that's the other rule of math, right? Same thing is true with parentheses in software. So you just want to make sure you understand that whenever there are parentheses, you can force a change. So this is where we're going to stop for the day. I want to give you a preview of coming attractions, and no, we're not going to figure all this out today and do a table before we leave. But let's take a look at this expression right here. Can everybody see this expression? Okay. So what we have here is a combination of Boolean operators. And what we've done is expressed what we would call a Boolean function. And we could actually write the statements, the coding statements, to recreate this in software. We can build it with logic gates, and we're going to show you that later this week. But what you know is that not is applied to whatever results after we do this. And since we said that and is represented by a dot, and it's mathematically multiplication, right? And this is or, and mathematically that is addition. Which two values do we tackle first? Do we do these first, or do we do this first? We and the y and the z, which is multiplying the y and the z, and then that output is added using or to x, okay? Let's say that again. The inputs for y and z are multiplied, because and is multiplication. That happens first because multiplication is the first in the order. That result is added or ORed to the input, the value for x, okay? And then once we get that answer, we're flipping it. So if what comes out of this is a 1, the not turns it into a 0. If what comes out of this is a 0, the not flips it and makes it a 1. And we're going to stop right there, because we're not going to, I don't want anybody running, screaming from the room. We're going to build up to this level of work, but we're going to take very basic examples first. So this isn't like, okay, on Wednesday, we're going to be diving into this and doing this all over the place. No, we're going to take more basic examples, but I just wanted you to see about the order of operations and give you an example of how the order of operations would look or work with a more complicated function, okay? We're not going to expect you to do this in a truth table right away, all right? Does anyone have any questions about what we've based on the information we've provided, does anyone have any observations or comments? Any questions or concerns? Everybody knows that if you haven't taken the assessment yet, you have until midnight tonight to get it done, yes? Okay, and if you couldn't do it before, it could be because if you tried to open it up after the 10 a.m. deadline this morning triggered, it wouldn't let you get in there, so. All right, we're gonna stop sharing. Stop recording. That's it for today. Thank you for joining us. We'll see you Wednesday. For those of you that are finishing your first attempt today of the Module 1 assessment, good luck.